To assume that A, we assume that A at present cosmic time is 1.
Yeah, that's...
Because in this way, if we take the magnification factor as 1 today, then when we say magnification factor is 20, it means it's 20 times what it was today. And if it is one half, then it's 1/2 of what is today. But we take the magnification factor to be 0 at the Big Bang. Big Bang, all the universe concentrated in one point. Yeah. So, but so this is, yeah.
You're taking a single fluid only when you're writing rho?
So it's only one fluid. We'll see mixtures in a moment. So it's only one fluid, to make things simple. Okay? Now, this is one way of solving the equation, especially good if you want to do it analytically. But there's an alternative. For example, if a convenient way is to work with a Raychaudhuri and energy balance. We write the Raychaudhuri equation in this form. Here I could have written the cosmological constant as well. But we write, this is the Raychaudhuri equation. We are writing it in terms of H, and we're using H now. H, what is H? Is the logarithmic derivative of the scale factor, which is called the Hubble expansion scalar. All these quantities, see, the purpose of the course today, just to give you as we say in Spanish, salpicada, like I would like you to be completely wet and washed in water. But now I'm just throwing a little bit of water here. I don't know how splash would be in English. It's just a splash of what is coming. Yep.
So what the thing that will lead to consider lambda over there? You are fine with without the lambda also. And in the inflator term, A double dot by A, the Raychaudhuri equation.
Slow, not so fast.
Slow and loud.
Not so fast, not so fast.
You are not talking with him.
Don't be relativistic when talking. Don't be talking.
I'm going to say, what is the thing that will lead to put the lambda over there? You are okay with these equations without lambda. You are okay with it. You put just plus and minus with rho. And
look, lambda, cosmological constant, is very simple. Some people want to put that in the left-hand side of Einstein equations, which would make it a geometric term. But I think it's more convenient to put it in the right-hand side as a source. And if if you take it as a source, then it's a fluid with a funny equation of state, with what is called the quantum vacuum equation of state. I don't like to say that because it's not quantum vacuum, because it's 120 orders of magnitude.
No, what is this point is asking that if you are comfortable without lambda,
yes,
without cosmological constant, then why it's necessary to put cosmological constant in these equations?
Well, for completeness, you can think of it as this way. The cosmological constant is allowed. It's allowed in Einstein equations.
Yeah, it's not harmful at all.
It's not,
Yeah.
It's not forbidden. It's allowed. It's consistent. It's correct.
yeah, this is consistent, but if I am happy with till now we are happy with that. Without that also.
Yes, you
till
can.
Now we are happy.
You can either put it or omit it. Now, for completeness, suppose that I always put it, and I say, if you don't like it, just set it to 0. It's just a parameter, it's just an extra parameter that is possible to write. Now, observations currently suggest that there might be a cosmological constant. We'll get to that. We don't know, right? There might be necessary.
For dark matter and all.
Dark energy.
Dark energy.
Even if you look at the term Raychaudhuri equation, you can say that, okay, we can explain this acceleration without this term also, because there are other two terms, non-zero, rho and p also.
Yes,
yeah,
you can do that very exactly. You can say, you can use this golden rule that this would be like a sort of total density and total pressure, and the cosmological constant will be part of this total density and the total pressure.
Yeah.
It's equivalent.
Yeah.
So I would rather be a little bit as how to say, eclectic in the sense of using different notations and different forms, not to be married with one. But as long as you understand what you are doing,
Yeah.
okay. So this, if we write the equations in this way, this is very handy for numerical work, because see, this, once you specify pressure as a function of density, then this system is a system that's very easy to integrate numerically, right? But once the system is integrated, what you obtain is h and rho. And once you have h and rho, once you solve this system numerically, then the scale factor follows by integration. See, you invert this relation, and this a logarithmic derivative. That's the exponent of an integral subjected to this condition, that h of this is a very convenient condition because it sets the standard of the scales to 1 today. It's setting a sort of ruler, right? Okay? And so this is very practical. This system is very practical for numerical work. Ready? Can I change to the next page?
So,
Yeah.
excuse me.
Yeah.
So this first equation is dimensionally consistent.
What?
This
Which
equation
one?
number one, Raychaudhuri equation. In the next
This
part,
one?
yeah.
Yeah, this is Raychaudhuri equation.
Yeah, this is dimensionally consistent, right?
Yeah. Yes, because
This means square.
h, the units of h is, no, h is 1 over centimeter.
In C equal to 1, so that is.
Yeah, but here remember that g, this is there has to be a g and a c fourth. I'm not writing the fundamental constants, setting them to 1. So the multiplication of g times an energy density divided by c fourth is 1 over centimeter squared, which is the same dimensions as h squared and the same dimensions as dot, because the dot will add a centimeter to the denominator. No, they are completely consistent in terms of units. Except it doesn't look like, because I'm not writing the fundamental constant. But you have to put a g here and a c fourth here. And once you put the right units on the g and the c fourth, and then remember that density is that rho is an energy density. It's ergs divided by cubic centimeters. We'll do that later. I'll show you exactly. No, they're absolutely consistent. Okay, so examples of equations of state. Let's look at several examples. Now, I have shown you that an equation of state has to be chosen, but which ones? Well, depends on the system. The very simple, every source will have an equation of state. It will depend on the source. Let's work with these two equations. Now, notice that I'm taking cosmological constant, but cosmological constant doesn't appear here because P plus rho cancels the cosmological constant, because the cosmological constant is like a fluid that satisfies P plus rho equals 0. So we take these two equations. Now, the simplest possible equation of state, the so-called gamma law. Some people, instead of gamma minus 1, they write a W. But it's simply saying that the pressure is proportional to the density. Gamma is a constant. If we take gamma equals 1, then pressure is 0, and we have what is called dust. If gamma is 4/3, then pressure is 1/3 of the density, and is what is called radiation. So if gamma is an arbitrary number, we have all sorts of possibilities. However, other than these two values, like gamma equals 1/2 or 5/6, has no meaning. They are just mathematical fluids. There are no physical fluids whose equation of state is P equals 5/6 of rho. But it's a nice mathematical model. So let's play along with it. See. First, we integrate this one, takes this form. See, we just substitute P plus rho, and we obtain this quantity. This is easily integrated because there are two logarithmic derivatives, a power law, and we get that density as a function of the scale factor has this very simple power law. Therefore, pressure will have this also very simple dependence, where P0, here the sub-index 0 means evaluation at present cosmic time, right? And then we can write the Friedmann equation in this form. It's a power law. These factors here are going to be defined here. But meanwhile, we can reduce this equation to this quadrature that can be integrated in this way. Now, rho 0, P0, H0 are the density, or here I say density, I mean energy density, right? Energy density, pressure, and the Hubble scalar at present cosmic time. And we have assumed that A of 0 is 0. We are saying T equals 0 is the Big Bang time. And we are also assuming that A evaluated today is 1. This means that all scales are, the way the scales are measured are compared to present cosmic time, right? If scales, if a given system, the A for that system was 1/2 at some previous time, we know it is 1/2 of what is today.
Sir,
Okay? Yeah.
actually I have two questions now.
Yeah.
One is, you are saying that this P by rho, I mean the equation of state, depends on the source, right?
Yeah.
Can you elaborate on it a little bit? I mean,
Yeah, there are many types of sources, and sources have information that is not contained in Einstein equations. Because suppose we're here, and we're doing an experiment here. We're at this 20 square meters. We can ignore gravity because we're in an in a equal potential. The gravitational potential Newtonian. We're in an equipotential surface, so we can ignore gravity. And so we look at the gas. And suppose that this gas, it's very diluted, so we model it as an ideal gas. Now, you bring a very degenerate Fermi gas here. We study it in the lab, so it has a different equation of state. And if we have a superconductor, it will have a different equation of state. And if we look at an electromagnetic field, which we can also describe as a fluid, as I will show you later, it has a different equation of state. Now, if we put gravity, this has to be valid, but we have to add the curvature terms. You see, this is the equivalence principle, that the physics locally, all the physics reduce to the way it is under special relativity. And when we incorporate gravity, it means that all derivatives have to be replaced by covariant derivatives. This is the equivalence principle. And so, since we have to correspond to local physics, in local physics, the equations of state of local physics are not determined by gravity, but by the inner workings of the molecular structure of the microscopics of the physical systems, right? So we have to. This is why different equations of state have to be incorporated, also in a way that is not prescribed by gravity. Gravity is not going to tell you the difference between your Bose gas or your Fermi gas or your superconductor, right? This is determined by local physics, okay? Not gravity. You can forget about gravity, okay? Now, when you put gravity into that, then you have to carry on this local information and put the extra geometry. Yeah, is this understood? This is important, right?
So here what you are taking as a means a source means you are considering gravity here in these equations.
Yeah, these equations incorporate gravity under the cosmological principle. But
Okay.
the assumption is that observers locally do local physics.
Yeah.
And the local physics is what tells you the equation of state. See, the local physics is telling you whether you have radiation or dust or whatever. What is radiation? It's a photon gas. Right? It's a photon gas. So the photon gas, you can study it without gravity also. Right? And then, but once you put gravity, then you have to put this information into Friedmann equations, and then you have a universe in which there's the local physics is radiation, but this radiation is evolving gravitationally because we are putting it into dynamical equations of gravity. Okay, so another question,
Yeah,
right?
The second question. Is it stupid to ask why are you not including any dark energy density parameters?
Take dark energy as cosmological constant.
That answers it.
Yeah. Yeah, of course. See, and it's not such a, it's a good advice because all the models of dark energy, quintessence, they're a bunch of crap. Still the gravitational constant rules over them and sees them with infinite disgust. So the best model for dark energy is the cosmological constant. Take it as that.
Why are people working so hard?
No, they're working, no, but no longer in quintessence. If you look, quintessence has already. We don't know what's dark energy, to be honest. We don't know. So every good attempt, every decent attempt is okay. But so far, to simplify matters, just think of dark energy as a cosmological constant, just to make it simple now. Okay. Another question?
Sir, you were saying that for gas, if you are studying it locally,
Yes.
then you are not involving the special relativity effects. Okay.
No, special relativity, yes.
But if you start involving them, then you must have the curvature of space. I mean to say that will the system be different if you keep a gas, if you keep a Fermi gas in a spherical ball, and in other case you keep it at I must say in uniform space, uniform.
Means it's flat surface.
It depends. The idea that you put the gas in a box, no. There are no boxes here. We're just thinking locally. It's just that if you have a gas, of course, the gas can extend over thousands of megaparsecs and so on. But the point is that if you make measurements, you can always make local measurements, and these local measurements have to be consistent with measurements of local physics in which gravity is not taken into consideration. That doesn't mean that you cannot put gravity into it, right? You can put gravity into it. But what I'm saying is that you can study all these thermal systems and many other even non-thermal systems locally without gravity. And once you put gravity, you have to put it in such a way that locally you reproduce the results of local physics. That's the point. See? Now, that doesn't mean of course you have to put gravity on it. And one way of putting gravity is by the equivalence principle, in which we substitute the derivatives, the ordinary derivatives, with covariant derivatives. We assume there is invariance under coordinate transformations and tensorial laws, and then we put the effects of gravity through Einstein equations. But the equation, the choice of equation of state, is a choice that is necessary in order to make the correspondence with local physics, right? Okay. Well, now what are these omega things here? See, these omega parameters are very useful quantity. Oh, I didn't want that. Oh. Sorry for the glitch. Now I just have to be careful what I push. Yeah, this one. Okay. These omega factors are one way of expressing the density today, right? The density today, how can you, suppose we're thinking about rest mass density. Which observation would you suggest so that we can have an idea of the rest mass density in our cosmic vicinity? What would you do? How would you estimate that? You have all the telescopes at your disposal. So what do you do?
You have to take average.
You
Respect to
count the
space.
sources. You count the sources.
Yeah, resources, and then take average with respect to space, which we are.
The average you can take afterwards, but
Afterwards.
first you have to do a number counting of
Yeah,
sources.
yeah.
It's a galaxy here, another galaxy there, there. I put them in different distances. How I estimate distances? Complicated problem in
Yeah.
astrophysics.
Yeah.
The distance ladder using standard candles.
Yeah.
But nevertheless, you can estimate distances with errors or whatever. So here I count all the galaxies, and I make estimates of the gas by different optical and radio telescopes and so on. And so I estimate this distance here. I can give a value, which is roughly, if we take very large scales, it's about 10 to the minus 30 grams per square centimeter. Very low density, the average cosmic density today. And we can also estimate the amount of photons by the CMB radiation. So we can do estimates. But another quantity that is very important is H0. H0 is essentially how far away are different galaxies or groups of galaxies expanding from ourselves. See? The units of H are normally, well, it's a sort of velocity, but the astronomers have a very tricky way to describe it. It's like, it's in units of 100 kilometers per second per megaparsec. You know what is a parsec, right? Somebody doesn't know what is a parsec?
1.26 light years.
Yeah, but what is it? It is the angle, is the parallax angle of 1 second. That is why it's called parsec, because the parallax of 1 second angle, how far is that away? It's 3.26 light years. Now, light years is mostly to tell the public. Because if I tell somebody in the public, a politician or somebody in the media or a celebrity, so here comes, I don't know, Julia Roberts, and asks me, so how far is it? If I say parsecs, you say, what? How do you eat that? But if I say light years, then it's understood. But technically, light years are not used. It's mostly parsecs is the unit. So if you are planning to go into astrophysics, you should start thinking in parsecs, in terms of parsecs. Now, what else was going to say is the issue. What was
Distance between galaxies.
Yeah.
Parsec,
It is H0 is how fast are sources receding from us in terms of the distance. See, it's 100 kilometers per second per megaparsec. That is that galaxies, this is something that has to be estimated. And the best estimate today is around 70 kilometers per second. There are some quirks about that, but roughly it's around 70 kilometers per second per megaparsec. That means if a source is 100 megaparsecs away, it's receding at 70 kilometers per second, right? So if the source is 100 megaparsecs, it's like 700 kilometers per second, no, or 7,000 kilometers per second. Anyway, it's a sort of linear proportionality, which is correct at up to a certain distance. It's not completely correct at very long distances, but then at very long distances, there is also a lot of uncertainty in the measurements. But nevertheless, these things here, it's the quotient between this density and 8 pi. Remember that there is a g and a c squared that is not appearing here. But this 8 pi over 3h0 is an inverse density that is called the critical density. The critical density because it's a density that is made with fundamental constants, g and c4 and c, together with this observational constant, and these numbers are of order 1. It's easier to work with a number if you are doing this integration. If I do the integration with rho 0, then I would have to use a horribly small number like 10 to the minus 32. On the other hand, if I divide the average cosmic density by the critical density, then I get something that is of the order of 1. And the same with lambda. And this is the so-called curvature, the omega of curvature, which is... Are you familiar with these equations, or you want me to write them in the blackboard? You are familiar, right? Okay. So cosmic H would be the integral from 0 to 1, and we get the estimation of cosmic H. Remember that all this is under the assumption of an equation of state of the form gamma minus 1 multiplying rho. This equation only makes sense physically for two values, for dust, which is gamma equals 1, pressure 0, or radiation. For other values, it's merely a mathematical model. And now, let's look at the more physical, because the previous equation of state is really a mathematical equation of state. Are you familiar with this idea of the critical density and forming the omega factors and so on? Are you?
Yes, somewhat.
Yes?
Yes, somewhat.
Yeah. Okay. Well, if there is a need, I will go back to that. Yeah.
Can you relate that curvature space-time geometry coupled with P correspond to 1, -1 and 0, open and flat universe?
Yeah.
And to this energy omega density parameter.
Yeah, yes, you can see it. If you look at the omega of the curvature, if the omega of the curvature is positive, then it's then the curvature of the space-like slices is positive. If it's 0, it's negative. It's measured by the omega.
Sometimes we solve the field equation for flat universe, flat FRW model.
Yeah.
But we get this omega factor 1 or -1.
Yeah, if you are working with a flat, say, if you are working with a flat FLRW model, then this means that the omega of matter plus the omega of all forms of matter, radiation, dust, etc., plus the omega of the cosmological constant, the summation of all of them will be 1, exactly 1. See? Now, these omega factors is something you can estimate by measurements. And so if you estimate them separately and they all add up to 1, then you can conclude that the space-like slices are flat. See, that's the way you conclude. It's not that you make triangulations or measurements of that. You simply add up all the omega of the different contributions, and this is what is happening now with the measurements. The satellites, either Planck, for example, or before Planck, WMAP, and all of them, they estimated these parameters and they summed them, and they tell you that the curvature of the space-like slices is almost very close to zero. But this is how they detect it, by measuring, by estimating the omegas of different contributions of cosmic matter, right? This is the way it's estimated. Now, let's look at some more, for example, a classical ideal gas. It's very good to describe baryonic matter or cold dark matter. See? Obviously, baryonic matter is better described as an ideal gas because baryonic matter is thermal. We're talking about protons, electrons, even neutrinos, photons. They are, well, photons and neutrinos are an ultra-relativistic gas, but let's say electrons, protons, they can be regarded as ideal gases. In fact, they are treated as ideal gases in the early universe. Of course, there are gas mixtures. Here, for simplicity, we're going to consider only one, not mixture, but only one ideal gas. And let's see how Einstein equations for the FLRW models look for this system. Now, this system is physical. Ideal gases are physical. Lots of systems behave approximately very well in comparison with an ideal gas, right? The gamma law that I showed before is a mathematical thing. This is a physical system. Now let's see how it works.
Excuse me, sir.
Yeah.
Just to clarify, cold dark matter means non-relativistic, right? Or
Yeah, it's non-relativistic because it's made of heavy particles. In fact, what we're going to see is a classical ideal gas. It's a non-relativistic system, but nevertheless it can be seen in general relativity. The equation of state takes this form. This rho here is, remember, that it's not just density. This rho is energy density in all its forms. See? If you are Newtonian, then for somebody who is Newtonian, only rest mass produces gravity. Everything else does not produce gravity. Only rest mass, right? But in relativity, there is a different outlook. Relativity, we're saying that every form of matter energy will produce gravity. This includes rest mass, but it includes also internal energy. See, this is the total. See, if you were Newtonian, you would only consider this as density, and you would call this internal energy. But here, we are going to consider rest mass density and internal energy density as contributions to the total energy density. And pressure, well, this is the, I don't know if you are familiar, here I'm writing K, it's here. N is the particle number density that has to satisfy this conservation equation, because let's assume that particle numbers are conserved. This is the current, the particle current, whose divergence is zero, right? So that means that number density is conserved. T is the temperature, and K is Boltzmann's constant, right?
So here in first term we are using E is equal to mc square equation, no? Energy density, first term, yeah.
Yes,
Yeah.
exactly. This is the mass of the particles.
Yeah.
Multiplied times c squared is the rest mass of the particles.
Yeah.
And you multiply them by the amount of particles you have per cubic centimeter, and you have the density of the rest mass density, right? And this is the rest mass density,
Yeah.
and this is the internal energy is kT. K is Boltzmann's constant, multiplied times T is an energy. That's the internal energy. And then you multiply times n, and you make it a density. Right?
Internal energy.
And pressure satisfies, this is the equation of state for the pressure in an ideal gas, right? If you've taken thermodynamics, you can immediately recognize it. You can write the small n as big N divided by volume, where big N is the number of particles divided by volume. The units are 1 over cubic centimeter, right? You've seen that. I'm sure you've seen that, right? Okay. Now, how do we? Looks like a more complicated equation than the other one, and indeed it is. So how do we incorporate this? Well, first we have two conservation equations. We have this conservation equation, and we have this one. So we have to work them together. And once we work them together, we get this constraint, n dot over n. That means that n, these are very easy to integrate. It means that the particle number density is diluting with the cube of the scale factor, right? Which is what we expect from a number density of non-interacting particles. Now, T is diluting with the square power of the scale factor. So now our Friedmann equation then takes this form. And look carefully. Here, what we are doing is using the omega of the rest mass. This is the omega factor of the rest mass.
Excuse me, sir.
Yeah?
I do not understand this.
Sigma?
No. This n dot. I mean, if ideal case we are considering, then n shouldn't change. So from where does the time dependence come
No,
from?
because it's a density. It's not the
So
number.
it can come from the volume.
Yeah, of course. Particles are conserved, but they occupy larger volumes or smaller volumes. So the volume, the dependence a to the minus 3 means that it's inverse to the volume because the particle numbers are conserved. See, essentially, it's where is the chalk here? Essentially, what you have is this. You can always write n. As number of particles by volume, right? So if this is conserved, then n will be proportional to the square of minus. So that's why it will be proportional to the cube of the scale factor, right?
Yeah, I have a question, sir.
Now, how do you obtain these equations? Here you have density and pressure, and you just plug them into the conservation equations. And then the conservation equations really look like this. See? Let me write them again. You have to plug this equation of state into these two equations. See, you have this equation.
Sir, I have a question.
Equals 0. This will say and this one will be just plug this equation of state into those ones and do some algebra, and you obtain this.
I have a question. Suppose I shoot a bullet, okay?
What?
I shoot a bullet in the air, okay, and then I consider this rest mass energy is first, rest energy, this mass energy is first, is taken care of this first term, this mc square m, and the internal energy of this bullet itself, this vibration, molecular vibration, which should be taken care of by this kT term. But what are the kinetic energy? How will we consider this? How will we incorporate this term? This it is moving also. It has some half MB spectrum, then how will we incorporate in that?
Sorry, what?
सांस लेकर के बोलिए आराम से.
My question is that I shoot a bullet in the air and
A bullet?
yeah,
Bullet, he shoots a bullet in air. Okay,
Okay,
now.
yeah.
yeah, so its mass term is taken care of by this first term.
Yeah.
Okay, and it's the kinetic energy, the internal motion of the molecules. It will be taken care of this by the second term.
Yeah, but to simplify matters, imagine that you are accompanying the bullet in the same reference system.
So that's why I put by the half MB square terms to 0. That's
Yeah.
why.
Yeah, if of course,
I cannot
if you look at
consider-
bullet passing by,
Okay.
then the bullet is going to be very fast. But this is we're assuming that we're assuming a moving frame.
That's why we can. So that term we are actually not considering. Only
No,
the
no,
one.
it's not zero. If you
It's
are
not
if you
zero,
are
yeah,
if you are
obviously.
riding along with a bullet, here's a bullet, and I'm riding along with it.
Yeah.
So the bullet is approximately still, but
Yeah.
it's not completely still.
But
So these small motions
Yeah.
are what make the pressure.
Yeah.
Okay.
And it can make our life simpler also by taking a closed system. Then if within that if we consider the bullet, then I think the kinetic energy of the bullet itself can be taken care of. This it will lead to the temperature.
You mean a collisional system?
Yeah. That,
Yeah, but
that can be taken care of. But in the closed open system, I cannot.
You don't need to, but because of course, if you take collisional systems,
Then can I take it?
then of
Okay.
course there is exchange of momentum in each collisions, and this also
Yeah.
creates a pressure. This also supports the pressure. Yeah, but then you have to use kinetic theory and collision integrals and so on. It's not necessarily for the
So I
purpose.
should coming from myself.
You can, and it's done normally in studying early universe, especially. You have to study. See, early universe is a mixture of collisional gases at very high temperatures. And the collision integrals are very important because particles are created and destroyed, and you have to check abundances and nuclear reactions and so on. So this is done for early universe, has to be done. But it's not going to be important for late universes,
Oh.
okay?
So this
Now-
is non-relativistic.
It's the thermodynamics is non-relativistic, but the dynamics is relativistic.
So the number density varies relativistic.
Eh?
The number density varies relativistic.
For example, if you take a photon gas, then your number density is not as simple as that.
Yeah.
If you take a Bose gas or Fermi gas in an ultra-relativistic or mildly relativistic regime, this equation of state is not valid anymore. How do you know if it's valid or not valid? There are several criteria. For example, if you compare the average intermolecular separation with the so-called the Broglie wavelength, the thermal wavelength, then you see that if your interparticle separation is much larger than the thermal wavelength, then you can use this type of equation of states, the Maxwell-Boltzmann gas, because quantum effects you can dismiss them. But otherwise, you cannot. See, the ideal gas is assuming that particles are non-interacting unless they collide, and the collisions have to be binary collisions, elastic binary collisions, which is a very big assumption. And suppose the particles, the collision times are huge, are enormous. So practically it's a non-collisional system, and this equation of state is still valid, right? And but if there are many collisions, if collisions are relativistic and so on, then this equation of state is not valid. But what we're doing here is we're taking a very non-relativistic equation of state, but describing it in terms of a relativistic dynamics. And the first thing we did here, if you notice, is that we are using a concept that Newtonians don't do, in the sense that what we're doing is considering the total energy density. We are saying, look, Newtonians, for you, the only thing that produces gravity is this fellow. But for us, all of them produce gravity. Right? And this is a major conceptual break with Newtonian physics. Do you understand? Newtonian physics, look at Newton's equation, the Poisson equation. divergence of the gravitational potential equals the density. Let's go to Newton's grave and say, "Hey, Isaac, wake up. What density did you mean?" And he will say, "Rest mass." Okay. Newtonian is rest mass. Only rest mass produces gravity. Now, here, even though we are taking a Newtonian equation of state, we are saying, no, Newton, you are wrong. Here we have internal energy that will also produce gravity, right? Okay? So, approximation for baryonic matter. But baryonic matter might, at higher temperatures, is not such a good approximation. Because, for example, in models that are considering warm dark matter, then this correction might be larger, maybe like 10 to the minus 2 instead of 10 to the minus 4. But it's still, dust is still a good approximation.
Excuse me. In your first equation, rho and T, you were mentioning that these, the second term, the 3 by 2,
This
and
one.
KT,
Yes.
it represents a relativistic term. Or that is not clear.
No, this is internal energy. It's
Internal energy, no? Yeah.
internal energy per particle in an ideal gas is 3/2
Yeah,
of kT.
yeah.
You multiply that times n, and you get a density. That's all.
That's all. And then first term it gives you relativistic thing, no?
This one? Yeah, because
Yeah.
you multiply by, that's true.
Yeah.
That's true. It's also because you multiply times c squared.
Yeah, because there we are using relativity, means E equal to mc square.
Yeah, the Newtonian would only use mass.
Yeah.
That's right. That's another difference. Like a Newtonian fellow will say gravity is produced by mass, not by rest mass, but by mass. Because in Newton's theory, there is no such thing as rest mass. It's always mass.
So these dispersion velocities are same as that of peculiar velocity.
Sorry?
These dispersion velocities, which you mentioned, are same as peculiar velocity of galaxy, or
They can be identified with peculiar velocity because a peculiar velocity is that velocity that is internal to the galaxy that is it's out of the commoving frame. It's a non-commoving velocity. So if you take a commoving frame, which is complicated in practice, because again, we're talking about large distances, large scales, where measurements are complicated, they are prone to errors and so on. Simply estimating distances is complicated. But once you have a reference frame, that you assume that you have all sorts of corrections into a rest frame, then you can say every velocity that deviates from that is a peculiar velocity. But the dispersion velocity is actually an average. It's a moment, it's a statistical moment. It's not simply the deviation. The peculiar velocity is just the deviation. But here we are taking the deviation, we square it, we average it, we compare it with the opposite, with the average, with the square of the average. See, it's the difference between the square of the average and the average of the square, and you square root that. It's a mean square root. It's a moment. It's a second moment, statistical moment of the velocity distribution, whereas the peculiar velocity is a simple deviation.
observed by a commoving observer.
They're of the same order. Yeah, they're of the same order of magnitude. One is useful to estimate the other. Okay? So, in the future, we're simply going to take dust. But when I say dust, I really mean a very low temperature ideal gas, right?
And pressure is 0 for dust always.
Yeah, dust is strictly 0.
Yeah.
But since the correction is very small, the correction of the dispersion velocities is very small, we will assume it to be 0. Now, fluid mixtures. So far, we've been looking at simple systems. Now, What happens if we have two types of systems? We have a mixture. Now, in this case, we can speak of the total energy momentum tensor being the sum of one source and the other. They are both coexisting. Now, the first question is, do they have to have the same for velocity? The answer is no. You can have a mixture in which how do you determine, like, for example, in the case of the universe, here we are, observers, cosmic observers. And if we believe Star Trek, there is the Vulcans are over there, and what are the other peoples who appear there, Herculeans or whatever extraterrestrial races are over there. We're all observers, happy observers of a happy universe, right? But this, we're talking about Mr. Spock or Captain whatever. Yeah? Yeah. Or the old ones, an old fellow. So I was. Anyway, these are actual people who are observing. They have their telescope. They make measurements. But what would be observers in a photon gas, or in a gas of baryons or cold dark matter particles? So, hi, you're a cold dark matter particle. Me too. So let's do observations. What do you observe? Blah, 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 we talk. That's not going to happen. Particles are not going to talk to each other. So, well, we don't know, but we don't know what's dark matter. Maybe dark matter is intelligent beings somewhere. We don't know that. So, what's the sense of observer in systems that are completely unpersonal? Well, essentially the comoving frame is constructed with the average of velocities. We have the particles; they all have very funny orientations and velocities, and there is a distribution of speeds, magnitude, but then there is also a distribution of angles. And so what we are assuming is that there is in every small element, small meaning that is sufficiently large so that you can do statistics, and sufficiently small so that it's that approximately macroscopic quantities are constant there. See, there is always a size of this type in every thermal system. Like if, for example, your interparticle, your collision times or your interparticle separation is, I don't know, the order of 10 to the minus 20 centimeters or 10 to the minus 10 centimeters, whatever. Then if you take like 5 or 6 orders of magnitude larger than that, it is still too small to have the macroscopic variations, the macroscopic quantities to be constant there, but it's large enough to contain a very large number of particles to do statistics. And you can always find an average velocity that for that cell will be representative of all of them. And this is how a comoving frame is found, right? And essentially this is also how we can, from all observations of galactic clusters, reconstruct a four velocity of a cosmological model. Now, what we do in case of a mixture? In case of a mixture, what we have is that the balance, the energy momentum balance, holds for the whole thing. It must. Why it must? Because Einstein equations are inconsistent if this doesn't hold. This has to hold. However, look, there are two possibilities. One possibility is that this holds separately for each component, in which case we have a non-interactive mixture. That is, each component is separately conserved. Therefore, there is no interaction between them. This is a non-interactive mixture. However, there's another possibility. This holds, but none of these are separately conserved. However, they have to satisfy this constraint. And this constraint means that that one source is transferring 4 momentum to the other source. So there is an exchange of 4 momentum between the two sources, right? And this is an interactive mixture, right? This yeah.
I have a question different out of context. Say, if the relative velocity between two particles are high, say for instance, and I say two co-moving frames for some observation with them. Okay, the two different particles, they have some relative motions, and I
Yeah.
say two co-moving frames on them. So it will, so for these things to for some observable, I require simultaneity for some physical observation. So will it maintain because they have some relative velocity. So yeah, I measure something over energy here, I measure the energy here. Can I sum algebraically?
No. You have to be careful. You can have two co-moving frames,
Yeah.
but one is co-moving, say, it's particles A, particles B.
Yeah.
So you have a co-moving frame A that is co-moving with this one, but
Yeah.
it's not co-moving with the other one.
Yeah.
Yeah,
Yeah.
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 Okay, but you can have the two particle species in the same co-moving frame.
Yeah, that's I do not understand. How can I do it?
No, but once you have one fluid mixture, one component of the mixture
Yeah.
with 1/4 velocity, you can always set up a co-moving frame with that.
Okay, yeah.
But
Then-
suppose the other mixture component has a different 4 velocity,
Yeah, yeah.
then you cannot have both co-moving.
Yeah, you cannot.
You cannot. You either have one frame in which both of them are non-co-moving,
Yeah.
or one frame that is co-moving with
With one, but
one
other is
family
co-moving.
but not with the other.
So
And
So
in
the
this
measurement-
case, you have to be careful because in this case, the interaction might be what is called a kinetic type of interaction. There is interaction simply because the other particles are moving away, and
Yeah.
therefore there is a momentum flux.
yeah, that was my point of objection in your this example of bullet actually. So
Yeah.
that's why I was telling that if I the relative velocity, I cannot sell simultaneously co-moving frame and sum them algebraically all the energies. That's it, because I'm taking my measurement in different frames.
Yes,
Different.
no, that's
Yeah.
true, that's true, that's true. That's true. Here, I'm going to see the case of
Yeah.
different frames later.
Yeah.
But as far as now, let's assume that the two components have the same 4 velocity.
Yeah, that I can actually tell.
Let's
That is
assume
the-
that for simplicity meanwhile. Okay?
Excuse me, sir. Can you repeat this again?
Yeah, all this,
No.
this.
Balance, yeah.
Yeah, here you have the two components of the mixture are not independently conserved. Means that conservation is non-zero. See, the divergence is non-zero. And this divergence is also non-zero, but one is a negative of the other, so that when they are summed, they are 0. Right? And in this case, we say that the mixture components are interacting. Okay?
So I think this is necessary and sufficient condition to be for delta TA be equal to 0, no? If this is equal to not, sorry.
Yes. It's you said work it in these terms of necessary and sufficient conditions. Like for example, this is a sufficient condition but not necessary.
Yeah.
And the same day, this is a sufficient condition but not necessary. And that's right. Yeah. The only condition that's necessary and sufficient is this one.
Yeah.
But these two are only sufficient, not
Yeah.
necessary.
Not necessary, yeah. Only sufficient. Yeah.
Only sufficient. Now, let's consider this case as an example. It's a mixture of matter, which can be baryonic. And when I say matter indistinctly, that means it's baryonic and CDM, right? Because cold dark matter and baryonic matter at large scales, cold temperatures, they behave very similarly. And it's just the question of the velocity dispersion correction, which for cold dark matter is maybe of the order of 10 to the minus 4, 10 to the minus 5. Maybe it's one order of magnitude larger when we're talking about baryonic matter. But it's a very minor difference. Now, here, the first component is an ideal gas. It's an ideal gas where this is the density and the pressure. Remember, I'm just substituting from the previous page. See, the pressure is essentially the mass multiplied times c. See, compare the difference of multiplying the mass of the particle times c squared and multiplying the mass of the particle times sigma squared. Sigma squared is much smaller than c. This is one of the pressure is very small compared. You know, pressure has units of energy density. Pressure is an energy density. But it's an energy density that essentially depends on the dispersion velocities, which are much smaller than the rest mass density, than the speed of light. So, and the second mixture, the second component, is a perfect fluid, but the equation of state is that of a photon gas. This mu0 is the Stefan-Boltzmann constant. You know that the energy density of a photon gas is proportional to the fourth power of the temperature. Here we're assuming whenever you see T, the letter T, it means the temperature of the radiation, right? This is a Stefan-Boltzmann law. Okay? You familiar with that? Okay. It's a black body experiments, and this is already known since Planck's time. Now, suppose if we have a non-interactive mixture, then this implies particle conservation. But the opposite is not true. We can have interactions that conserve particles, right? But if there is no interaction, then particles have to be conserved, because there is no way, in order to destroy particles or create particles, you need interactions, right? If there is no interaction, then particles are conserved, right? And then, so we apply this, again, shit, this thing is really annoying. This thing is really annoying. Okay, I'm sorry that all these glitches. Okay. Now, if we apply this, what we do is we apply the conservation laws, the energy momentum balance and the particle conservation law, and we get these conditions, we get these equations. It's the same as what I did here. It's these equations, but for this, what will happen is that since the four velocity is the same, the Friedmann equation will have the contributions of all the components. So the effects of the mixture will be felt in the dynamics, which is the Friedmann equation. See? The conservation equations are these ones here, will give all these quantities here. Essentially what they tell you is that the number density of particles scales inversely to the volume. The velocity dispersion and the temperature, they scale in the same way. Now remember that the temperature of the cold dark matter is the square of this, and this is the temperature of the radiation. And when we put all these things together into the Friedmann equation, we get this very nice Friedmann equation for the mixture. Now, since, as we have seen, the correction of the dispersion velocity today is of the order of 10 to the minus 4, so the Friedmann equation is approximately equal to a dust plus radiation equation of state. And here you can see how such a mixture, for example, the radiation today is not important because radiation dilutes much faster than matter, right? So this term, evidently this term is going to be much smaller than this one. And this term, well, if there's cosmological constant, then this term might be dominating the dynamics today. We'll go back to just a minute. And here we have all the omega factors, which the omega factors are quotients of an energy density to the critical density. So we do these things in order to get manageable numbers for numerical analysis or for understanding, right? And not to work with very big numbers. And this is the curvature. It's under this approximation. See, we determine whether the universe is spatially flat or spatially curved by looking at all contributions and adding them up. And if they are very close to 1, this means that the universe is almost flat. But what I'm trying to show you here is that here, what is the effect of the mixture is to obtain a more complicated Friedmann equation where all the mixture components will be inputted, right? Now, this is, of course, the case where the force velocity of the mixture components is the same. It's not necessarily a realistic situation. It's realistic at very large scales. Because at very large scales, we can say that there is a sort of, here I'm speculating because we don't know. Suppose we know that the CMB, cosmic microwave background, is a photon gas. So we can somehow assign a comoving frame to that photon gas. So we don't know if, suppose we do the same thing with cold dark matter. We don't know if cold dark matter, the average velocity of cold dark matter particles, coincides with the average velocity of these photons. The most likely event is that they do not coincide. Now, some people say, well, they don't coincide, but they're very similar, and the difference is very small, much smaller than the speed of light, but we don't know. But it's what most people would say is that at very large distances, it is safe to assume that all these different constituents of the cosmic energy density are roughly moving with the same force velocity. But it's something we really don't know, and it's worth looking at carefully. Now, the concordance or a lambda CDM model, it's what happens, for example, if the omega of matter is the sum of the omega of cold dark matter and baryonic matter, and it is smaller than 1, but baryonic matter is much less than cold dark matter by a factor of 1/20, or 1 to 20, or 1 to 10 at least. And then we say that curvature is almost 0 because what we see is that the omega associated with the acceleration of the universe, or dark energy, whatever, is roughly 1 minus CDM. So if we add them all, if we form the curvature, it's almost 0. This is the reason why we think that the universe is very close to spatial flatness, because all the omegas of the different components add up to almost 1. And people like 1 is a very nice number for physicists. Like if I say the sum of all these quantities is 1, that's very elegant, very neat. So people think it's correct because of this reason, but they, strictly speaking, don't know. I'm about to finish. Yeah? Now, all these, the numbers that people assume that fit current observations are that cold dark matter is 0.28. This is like 0.05, like 5% of critical density. This is like 1/1000th of and this is like 2/3, and this is, so this is more or less what fits the observations. And then the Friedmann equation that we obtain for this system is this one that you can see here. I'm afraid to push it here. Okay, you can see it there. This is the Friedmann equation, and that for this model, the lambda CDM model or concordance model. It's called concordance because this model fits very nicely with different observational tests. And it's very nice, except that we don't know what's dark matter, we don't know what's dark energy. So if you see cosmologists pontificating, wow, we are on the top of the world, we're invincible, we know what the universe is made, precision cosmology, quack, 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 quack. You just ask them, yeah, very nice, so what's dark energy? So what's dark matter? Big egos? No, in reality, no, you have to be critical. See, you have to be very critical, because Gauche and I are old farts, so we are already very vitiated, and we will say, yeah. But you are young people. You should be very critical. You should take all these big egos and say, now you say that, so what is dark energy? Explain that. How are you going to measure it? Because we really don't know. So we call dark all these dark things as a measure of our ignorance. So I don't know what's this, but the fact that I've given it a name, but that's not the end of the job. See? So now this is the model. It's called concordance model because it fits very nicely, many observations, and probably is the right model. But don't be fooled when people say, yeah, that's a model. No, we don't know. As long as we don't know what's dark matter or dark energy, then it's a big thing not to know what's that. Okay? So be critical on that. That's my advice. Now, in observations, what we measure is what we see is light, and the indicator, what we really measure is redshift. There's a galaxy over there. I measure the redshift, right? So redshift is it's a quantity that is very well measured. Now, how to compute the redshift from a given source? Well, it depends a lot on the model, right? But if we assume that the source and I are roughly existing in a Friedmann, Lemaitre, Robertson, Walker universe, then it's very easy to obtain a redshift formula for the Friedmann, Robertson. You can see it there. Essentially, the scale factor is inversely proportional to 1 plus z, and this in such a way that redshift 0 is for present cosmic time. See, since we have normalized the scale factor to be 1 at present cosmic time, then we want redshift to be 0 today, because if remember that the source is far away, it means that it's also further back in time, because we are looking at the source through a light ray. It's already erased that, but it's through a light ray, right? So once we do this, then we can transform all these integrals into redshift integrals. See, and this is, for example, the Friedmann equation integral for a lambda CDM model, and of course cosmic H is obtained from. See, here what happens is that A equals 0, A will equal 0 for Z equals infinity. See? So the further away an object is, the more redshifted will it be. In the extreme case, when A goes to 0, the redshift will go to infinity. But to perform this integral, we cannot put the lower bound in minus infinity, or we cannot put it in. See, there is a minus sign in the integral, right? So, so the lower limit of this integral is some initial z of an initial time, right? And what we can say is that cosmic H is obtained in the limit when this initial, it's a change of variable. It's just a change of variable. But since the variable is the inverse of the other, so we have to play carefully with the limits. Now, once we have this, we can see what is the effect for different FLRW models, right? Assuming that that the sources of we're going to assume two sources, cold dark matter and cosmological constant. And we are going to play with different omegas, and we can obtain, for example, plots of this type. This is the integral. We're assuming that omega curvature is the sum of the components minus 1, right? So as you can see, we compute cosmic time the way I showed before, and you obtain this numerical graph. Now the lambda cold dark matter, it gives a prediction of cosmic time of about 13.8. And this is the prediction. The open Friedmann-Robertson-Walker is a Friedmann-Robertson-Walker model with negative curvature but zero cosmological constant. And the flat one is zero cosmological constant and zero curvature. What we have is these values, see? For current estimates, as I was telling you, H0 is about 70 kilometers per second per megaparsec, right? Now, the lambda CDM model with these numerical values of the parameters will give you a cosmic age of about 13.8, 13.7 gigayears. Gigayears is 10 to the 9 years. Is the so-called Anglo-Saxon billion. The English-speaking world, they say billion, they really mean thousands of millions. Now, the open Friedmann-Robertson-Walker, the prediction is 11 gigayears. Here, omega lambda 0, but there is curvature. There is very large spatial negative curvature. And this is the so-called Einstein de Sitter model, which there is no cosmological constant, there is no curvature. And this is important because we know that the oldest stars that we observe are of the order of 12.5 gigayears, right? How do we know that? Because by looking at the breaking point from the main sequence in globular cluster stars. This is very interesting topic in astronomy. It's called isochronometry. I'll explain in a minute why it works. But nevertheless, this is an important constraint because the universe cannot have objects that are older than itself, right? We accept that, no? So this means that these two models are ruled out. Well, that doesn't mean that all this idea of the lambda CDM model is correct, etc., etc. Because here, notice that we are assuming an FLRW geometry, right? I already explained that assuming an FLRW geometry locally is very bad approximation. But assuming it at larger distances, it's a good approximation. So once we are doing this, the observations point out that these two models are gone. The only FLRW model that is consistent with observations is a model that incorporates some form of either dark energy or cosmological constant. I'm not saying that has to be cosmological constant. Some people have tried to model the effect of this. Here I'm modeling it by a cosmological constant, but some people say no. It doesn't have to be. It has to be some scalar field or some funny thing that will be asymptotically constant. Fair enough. That's okay. These are the quintessence models and so on. But in order to satisfy H constraints, and there are not only H constraints, supernovae, a lot of observations, we need to have something that is actually accelerating the universe. And so you can even see it at a very simple level. This is the very simple level, just looking at the cosmic H prediction of different models, right? So I think that this is sufficient for today. Tomorrow we're going to see basic theoretical, we're going to see Einstein equations in more generality. We're going to see cosmological models, space-time symmetries, how to, more general models than FLRW, but still models that are characterized by symmetries. And we're having also a computer algebra workshop. Now, after lunch, would like to show you some computer algebra examples, okay?
Is it possible today 3 o'clock? Because these people can come only at 3 today. They have prayers. They have to go for prayer. What time you can come back? 2 o'clock. 2:30 is fine? 2:30 is fine? 2:30. We have arranged lunch for all those, right? Registered participants. We have done arrange the lunch. And you can come back at 2:30 then. Maple for maple demonstration. Right? All right? Is it fine? 2:30 fine? Na? और कोई